Now let us discuss the exercise set for Chapter 3 bivariate data. In this notebook, Problem 1 and Problem 2 about Chapter 2. Now let's begin Chapter 3 exercises, and here we go. The following data table was obtained by a 4th grader on his science project, Exploding Foam. He poured 1/2 teaspoon of baking soda and 1/8 teaspoon of laundry detergent into 1/4 cup of vinegar of various temperature and measured the volume of the foam that rises. And here's the data set. Problem number 1, or more precisely, 1A, talks about the means and the standard deviation that we already did in the previous exercise. This is just for review, so here we go. This is the mean of x, or mean of the temperature, and this is the mean of y, the mean of the volume. Here is the mean of the temperature. Did I say mean? Sample standard deviation of the temperature. The sample standard deviation of the volume. Now, this is correlation coefficient, but that's something we'll discuss in the next set. Mathematica's computation yields these kind of numbers. X bar, y bar, those are means. Xx, sy, those are standard deviations. And we did all those in the previous example. Now, let's go to correlation coefficient. How do we calculate correlation coefficient? It goes kind of like this. We calculate the deviation of x, that is 45.5 minus the mean temperature, times the deviation of y, 250 minus mean volume. We do that for this one. And we have to do the same thing for this one. So deviation of the temperature, 41.4 minus the mean, times 175 minus the mean. Do the same thing with this one, and so on and so forth, until the very last moment here. Here we go. Deviation of the temperature times the deviation of the mean. Add them all up, that's the numerator, and the denominator is n minus 1 times sx times sy. Sx and sy are sample standard deviations. Maybe it would look better if I increase the font. Oh, too big. Yeah, okay, that looks a little bit better. Okay. And here is Mathematica's computation, because calculating something like this with handheld calculator, oh come on, forget it, that's impossible. Now, not everybody has expensive software like Mathematica, so let me show you a little bit more standard way, that is MS Excel. Now let's go back to the same data set we discussed before. Temperature and volume, and we use this Excel spreadsheet to calculate the mean, standard deviation, and then 5 number summaries and so on. Couple of blank spaces here are correlations. So let's calculate correlation with MS Excel. As usual, we go to the sigma, upside down arrow to get more functions, and let's go to statistical. Maybe it's in some other place. You can go to this upside down triangle and look for statistical and look for correlation. Go to letter C right here, correlation. Now you have correlation of 2 data because this is for bivariate data. So we need array 1 and array 2. Array 1 here, array 2 down here. Okay, first array, that's going to be the temperature. I select it with my mouse. Now let's click array 2. The second array is the volume. Okay, we are ready. Click OK. And there goes the correlation. 0.84719. Do we have the same thing as Mathematicas computation? Yes, indeed. That cannot be coincidence. That must be right. Let's repeat this once more, just for an exercise. Now, let's use this box for correlation computation. As usual, sigma, more functions, statistical here, and let's go to correlation. Now, previously we used array 1 as temperature, array 2 as volume, but this time let's switch it around. Array 1 for volume, and array 2 is the temperature. Will that make any difference? No. We have to have the same thing. Why? Here we go. The deviation of the temperature times the deviation of the mean, and that repeats everywhere, all the way in the numerator. And the multiplication is commutative, so this times that versus that times this, we have to have the same. How about the denominator? Sx times sy versus sy times sx, they are the same. Multiplication is commutative. So it does not matter whether you select array 1 as temperature or array 2 as temperature, and vice versa. Even more so, we have this correlation computation for temperature written in Celsius versus volumes in milliliters. Will that create a difference? If you do the same thing, no, it will not. We have the same correlation. How about the mean? Mean for Fahrenheit, mean for Celsius. Of course they are different. Standard deviation for Fahrenheit versus standard deviation of the Celsius. Different. But surprisingly for correlation, they're the same. Even if we select different unit, correlation remains the same. Now here we have for milliliters only, but if I change it into quart or something, that can be a little bit tedious because I have to convert those 19 times. But even if I did all those and calculate the correlation will remain the same. It's kind of strange. Actually, did I say strange? There's nothing strange about that. It's just a little bit more advanced, that's it. A little bit advanced property of correlation coefficient. Correlation coefficient does not depend upon the unit, measuring unit. Metric or English or other kind of units do not affect correlation coefficient. Now, scatter plot. This is what scatter plot is all about. X coordinate is the temperature in Fahrenheit. Y coordinate is the volume in milliliters. Each dot represents a datum. For example, this one is the 41 degrees and 175 milliliters is this one. How about this one over here? 42 or something and 500 milliliter. Kind of outlandish one. Yeah, this one. I think it's this one. Yes, 44.1 degrees, yet 500 milliliters. How about something like this over here? This dot looks kind of strange. As a matter of fact, this is not one dot, but these are two dots that are so close nearby. As a matter of fact, those two dots corresponds to these two. 52.0, 300, 52.4, 300. So they're so close nearby, these two dots kind of stuck together, and they kind of look like a snowman or something. As you can see, these dots are scattered around a certain hypothetical line, which is going up as I move to the right, and consequently, I can deduce that the correlation is positive. It is rather strong positive because the correlation coefficient is 0.7 something. It's pretty strong. So the kind of line of best fit, which is going up, positive slope, is readily visible in this example. Now, what exactly do I do with the line of best fit? That's going to be discussed in the next video.